Hello, everyone. Welcome to lesson 3-1. Today, we're going to be talking about conjectures and counterexamples, and our notes will be on page 153. We have two lesson goals for today's video, and they are to write and analyze conjectures by using inductive reasoning and to disprove conjectures by using counterexamples. So, inductive reasoning is the process of reaching a conclusion based on a pattern of examples. When you assume that an observed pattern will continue, you're applying inductive reasoning. And you can use inductive reasoning to make an educated guess based on known information and specific examples. And this educated guess is known as a conjecture. So in example one, we're asked to write a conjecture that describes the pattern in this sequence, and then use that conjecture to find the next term in the sequence. So we're going to look for a pattern in the times, which are 8:30 a.m., 9:15 a.m., 10 a.m., and 10:45 a.m. And of course, we can see where the arrows are drawn that we're adding an additional 45 minutes each time we go to a new timestamp. Just as a for your information, this is an example that shows what's known as a constant sum. In algebra, we call this an arithmetic sequence. But as we look at the pattern, we see that each appointment time is 45 minutes after the previous appointment. And so the next appointment time will be at 10:45 a.m. where we left off, plus another 45 minutes or 11:30 a.m. So for the check, you're going to write a conjecture that describes the pattern in the sequence you see here, 1/2, 1, 2, and 4. And then, of course, the dot, dot, dot there, ellipsis means that the pattern that is established in the previous terms is going to continue in the next number in the sequence. And so take a pause on the video and see what you can come up with for the answers here. All right, I'm on page 154, and I am being asked to make a conjecture about the sum of the squares of two consecutive natural numbers. Let's talk for a second about what natural numbers are. Those are going to be positive integers. So when you think about integers, those are your kind of tick marks down a number line. So whole numbers and their opposites. Natural numbers, if we say positive integers, remember that does not include zero there. So two consecutive natural numbers would be one after another. So the counting numbers, basically. We're going to list or draw some examples that support our conjecture. So if we take the first two natural numbers, 1 and 2, and we add their squares, we have 1 squared plus 2 squared, which would equal 5. We have 2 squared plus 3 squared, 4 plus 9, which would equal 13. We have 6 squared plus 7 squared, which would be 36 and 49, or 85. And we have 10 squared plus 11 squared, or 100 plus 121, so 221. And if we look at for a pattern in the outcomes of these sums, we notice that all the sums are odd numbers. And so we're going to make a conjecture. It says the sum of the squares of two consecutive natural numbers, we're going to conjecture that that is an odd number always. Take a pause in the video here to make a conjecture about the sum of two odd numbers. And in example 3, we start to make conjectures on geometric ideas. So it says make a conjecture about the relationship between the segments joining opposite vertices of isosceles trapezoids. So first of all, what is an isosceles trapezoid? An isosceles trapezoid is a trapezoid with two opposite congruent legs. So you can see the tick marks on this first figure right here. These would be the legs, the sides that are not parallel in the trapezoid. And so we would see that they have tick marks on them. Now, your book actually has single tick marks on every other pair of legs of the trapezoid, but please make the adjustment here because if we have single tick marks across all three of these diagrams together, then actually what that conveys is that all of the legs are the same length, and we can clearly see that that is absolutely not true. So adjust those tick marks, please, so that you can have that be correct. So what we're noticing as we make this conjecture that the pattern seems to be that the segments joining those opposite vertices appear to have the same measure. And we could put a ruler or a compass down to confirm this. So the conjecture we're going to make is that the segments joining opposite vertices of an isosceles trapezoid are congruent. And I'm here for the check on example 3 that's at the top of page 155. New concept of geometric context here, but you're asked to make a conjecture about the relationship between AD and AB if C is the midpoint of AB and D is the midpoint of AC. All right, in example 4 on page 155, we're being asked to make conjectures, or again, guesses that are based on patterns about a table of data. So we have the data here is about gas prices, and it shows the average price of gasoline for the years 2010 through 2018. So based on that pattern, we're asked to make a conjecture about the price of gas the next year, 2019, and explain how that conjecture is supported by what we see in the table here. So if we compare year to year, we can see that from 2010 to 2011, our price went up, and from 2011 to 2012, it went up again. I'm just putting a plus sign for it. We had added a certain amount to it. In the next year, the price actually went down and then down again, and then down even more, and then down again. But after that, it started to increase again and increase again. So what is the pattern that we are seeing, if any? Not a whole lot we can tell here other than that the price of gasoline is increasing at first and then decreasing again and then increasing again. So it seems to show that the price of gas follows what's known as an oscillating pattern, meaning it increases and then decreases, kind of back and forth. So the conjecture that we might make is that in 2019, the price of gas will continue to increase if we think about the pluses and minuses. We had two pluses and then four minuses and then two pluses again. You might consider to continue the plus pattern a couple more times, a couple more year jumps before you go back to decreasing. So that's what we can conjecture here. Okay, for the check on page 155 of example 4, we have a new table, and this is about an idea of hearing loss. It says 50% of young adults between the ages of 12 and 35 years old are exposed to damaging levels of sound from the use of personal electronic devices. The intensity of a sound and the time spent listening to that sound highly affects the amount of damage that can be done to someone's hearing. So we have a table of decibel level on the left and the exposure in time. So this is comparing how long it takes for a decibel level to do damage to a person's hearing. In the continuing description here, it says the intensity of a sound is measured in what are known as A-weighted decibels, so dBA. For every 3 decibels over 85 decibels, the exposure time is cut in half. So we're kind of told what the pattern is. How long does it take to cause hearing damage at 106 decibels? So we started at 85 and we go up in decibels 3 at a time to 100, we're asked to continue, we're asked to continue this pattern forward until we get to 106 decibels. So we're going to write our answer as a decimal in minutes. Take a pause on the video and see if you can figure this out. Okay, time for our second learning goal for today, and that is about counterexamples. So we've talked about how to continue a pattern forward to make a conjecture. And to show that a conjecture is true for every case, you have to actually prove that that is true for every case. However, it only takes one example that contradicts the conjecture to show that it is not always true. And the example that you find to contradict the conjecture is known as a counterexample. That counterexample could be a number, could be a geometric drawing, could be just a statement. But if you find one that proves the conjecture is not true, then the conjecture is false. So I'm on page 156 if you've lost track, and we are at example 5, where we're trying to find counterexamples for these beginning conjectures. Conjecture A says, if n is a real number, then negative n is a negative number. And then conjecture B says, if angle ABC is congruent to angle DBE, then angle ABC and angle DBE are vertical angles. So for statement A, our counterexample is actually a number. If n is a real number, then negative n is a negative number. Well, that's not true if n is itself a negative number. So a counterexample might be here -4. If we take negative n, that's -4 or 4, which is a positive number. So that would prove the conjecture false. So -4 is a counterexample. And for conjecture B, assuming vertical angles is not a safe assumption to be able to make, and you can see that by drawing a diagram that contradicts this. So while we do have in this diagram our arc markings here on angle ABC and angle DBE, it does not necessarily mean that that has to come from two intersecting lines making those vertical angles. So it says when points A, B, and D are non-collinear and points E, B, and C are non-collinear, the conjecture is false. And so the figure itself, um, we have the angles congruent, but they are not vertical angles. So you can see the counterexample here comes in the form of a diagram. Okay, for our last check of our video here, take a pause. We're on page 156, and you're asked to find a counterexample to show that each of these conjectures is false. Part A says if n is a real number, then 1 over n is less than n. And then we're given some counterexamples and selecting those that would be counterexamples to that conjecture. And then for part B, if a line intersects a segment at its midpoint, then the line is perpendicular to the segment. And this time, as before, we're asked to draw a diagram to represent the counterexample. Okay, everyone, this is the part of the video where you really want to check back on the answers to those checks that were assigned to you as you were watching. Okay, going back to the beginning, check on page 153. We're writing a conjecture that describes the pattern in this sequence from 1/2 to 1 to 2 to 4. Hopefully you can see that what we notice is that the next number in the sequence is twice the preceding number. And so the next number in the sequence would be taking 4 and multiplying it by 2 again to get 8. In example two's check on page 154, we are making a conjecture about the sum of two odd numbers. So let's pick some odd numbers. How about 11 and 15? If we add those two odd numbers together, we get 26. Pick another case. How about 27 and 33? We get that sum is 60. And we'll just go even more simple. Just 5 and 9, 14. All of these numbers here are even. And so the sum of two odd numbers based on this pattern, our conjecture is that it is always an even number. All right, reading through our check for example 3, and we are on page 155. We're looking at drawing a diagram so that this is true about the lengths of these segments. So first of all, we're told that C is the midpoint of AB. I'll start with a nice long segment, AB. So C is the middle there, and we'll go ahead and make that, let's go with, I don't know, let's go with 12 units long. And that way we know that this right here is 6 units and 6 units again, just giving it a value and letting it follow that, C being the midpoint. Now D, we're told, is the midpoint of AC. So we'll add this point right here in the middle. And so if we think about congruent pieces that that point D splits segment AD, or excuse me, AC into, we now have 3 and 3 for the length there. So if we think about what AD is in relation to AB, AD is 3, and AB, remember we said we started with the full length of 12. So 3 out of 12 gives me that it is 1/4 of AB. You could have started with any first number, but then relating those pieces once you put the midpoints in. No matter what you start with, that fraction will be the same. Our second check on page 155. Remember where our table left off was at 100 and 1/4. And we need to go forward to 106 decibels. So that's 2 more jumps on the table. Remember, we're taking half the amount of time for each new 3 decibels in loudness. So we have 1/4. Half of that would be 1/8. Half of that again would be 1/16. So my 106 would take 1/16, but that's of an hour. So remember, our units here are minutes, so we would want to use a conversion factor. So there are 60 minutes in 1 hour. That's so that my hour units will cancel out. And so I'm looking basically for 60 divided by 16, and that comes out to be 3.75 as we're writing our answer as a decimal. 3.75 minutes. You guys, that's about one song's length. Yikes. Be careful with how loud you listen to your music. Eeks. And then our last check, we're here on page 156. So for the check for counterexample A, if n is a real number, then 1 over n has to be less than n. Let's see if that's true. If we use n is -3, then we're looking at -1/3 being less than -3. Is that a true statement? Is -1/3 less than 3? Because that is false, then A is a counterexample. B, we would have 1 over 1/4, which would be less than 1/4. A reminder that when I think about dividing by a fraction, it's the same as multiplying by a reciprocal. So this actually comes out to be 4 is less than 1/4 for choice B, which is false. So B is a counterexample. If we look at choice C, we're saying that 1 over 1 is less than 1. Well, 1 over 1 is equal to 1, so that would again be a counterexample because that's a false statement. If we look at D, we are looking at 1 over 5 being less than 5. Well, that's true. And then 100 as our counterexample, 1 over 100 is less than 100. So it looks like we have choices A, B, and C that qualify as counterexamples. For part B, if a line intersects a segment at its midpoint, then the line is perpendicular to the segment. So here's our segment, and here is our midpoint. Let's call it point M. We know it's a midpoint. We can put some tick marks on that segment. Let's say that it's segment AB. It says a line intersects that segment and is perpendicular to it. We need to draw a diagram so that we're going through the midpoint, but not perpendicular. So here's our line. And if we are lacking that right angle box in the space around that vertex M, then it is not perpendicular. So here's a very quick counterexample drawing. All right, that takes us to the end of our checks, so we'll see you in the practice.